Okay, we are going to have a screencast here where I will create the solution for the worksheet that you guys did for homework tonight. And it's a AP style question with kind of a lab twist to it where you had to graph some information and use the slope to get an answer. So a dart of mass m is accelerated horizontally through a tube of length L. Okay, so the dart has a mass of m, and we're at height h above the ground, and the force acting on it is a constant force of magnitude f, and the dart travels, once it leaves the tube, a distance of delta x horizontally before it strikes the ground, as shown in the diagram. So all of those variables that are given there, we can use as given information as we solve the problem. But notice they do say in part A they want us to develop an expression for the velocity of the dart v as it leaves the tube. So this velocity v at that instant in terms of delta x, h, and any fundamental constants. So fundamental constants would be something like little g, which usually comes into play in these kind of problems. So our answer can only include delta x, h, and a fundamental constant like g, nothing else. What we're going to do is we're going to use what we've learned about kinematics and maybe some energy, fundamental principles of energy, conservation of energy, to solve this particular problem. Okay? Okay, I just wanted to clear the ink off of that page. So we want to develop an expression for the velocity of the dart, and what we're going to use is the kinematic equations. We know the initial velocity is all in the x direction. So we have a Vx there. It's equal to displacement over time. I need to come up with an expression for time in terms of h and a fundamental constant. Well, remember we've got an expression or a kinematic equation that looks like this. The initial in the y direction times delta t. Because it's coming out perfectly horizontally, my initial velocity in the y direction is 0. Which is handy because what that means is this whole part of that kinematic equation becomes 0. So I have a much simpler way to derive time in terms of delta y and acceleration. Well, acceleration is just my fundamental constant g. Delta y is the other one I'm allowed to use, which is h, right here. So solving for delta t is equal to the square root of 2h over g. So I can substitute that in over here, and I can have an expression for initial velocity as the delta x over square root of 2h divided by g. Okay? So that would be the answer to part A. I'm going to go ahead and clear that ink so that I can scroll down to B. Okay, so for part B, it says derive an expression for the kinetic energy of the dart as it leaves the tube in terms of these things here. Mass, delta x, height, and any other fundamental constants. Well, the kinetic energy is just 1/2 mv squared. We've already got an expression for the initial velocity. I'll put i's there for initial kinetic energy and kinetic initial velocity. My initial velocity is all in the x direction, so I can just use that expression that I derived in part A down here. So my answer here would be k initial equals 1/2 m times that quantity squared, which is going to be delta x squared, and then everything in the denominator comes out of the radical sign. So I could actually simplify this a little bit, and I could say mg delta x squared over 4h. So I put the g up in the numerator, and I multiply 2 times 2 to get my 4 in the denominator. Okay? So that would be an expression for the initial kinetic energy in terms of m, h, x, and that fundamental constant. All right, next part. Actually, I don't need to clear that because it's right here. Derive an expression for the work done on the dart in terms of F and L. that's easy. Work done, you know, on an object is just a force times a displacement, as long as the displacement is parallel to the force that's being exerted. So that's just going to be F times L. That's pretty straightforward. Notice how each step is going to build on the one before it. So now when we get down to part D, where it says derive an expression for the height of the tube above the ground in terms of all these other things that you just have used in previous parts of this problem, we're going to apply some of the information that we had before. Okay, for part D, I've already done it. Derive an expression for the height of the tube above the ground in terms of those things. Looking just at the beginning of this problem, you know, the work done by the force inside the tube over length L, this work right here, took the dart from 0 kinetic energy to the kinetic energy it had right when it left the tube. So I'm going to scroll up for just a second here. So the work done on the dart over this length, there was work done, and it gave the dart some initial kinetic energy as it left the tube. Okay, so that work done, assuming there was no non-conservative forces, or that the work done by the conservative forces is considered already in that net force, I come up with an expression: work done equals the kinetic energy. The work done is F times L. That was from this part up above. The kinetic energy that work gave to the dart is from part B. So I just set that equal to the work done, and then I solve for H. So I get this kind of funny looking expression here for the height in terms of m, g, the fundamental constant, delta x, f, and L, as the problem had asked me to do, you know, right here. Okay. Well, I'm going to use that in the second part of this problem, so I'm going to copy that to the next page as we try to solve the lab part of this. Okay, here's the relationship I had on the last page. Use a grid below to plot a linear graph of delta x squared as a function of L. So L would be on the independent axis because delta x squared is a function of L, so that's the y value. Use the empty boxes in the data table as appropriate to record the calculated values that you are graphing. Label the axes as appropriate and place the numbers on both axes. I will do that offline. Okay, so what I did is I squared all my horizontal distances because they want me to graph x squared as a function of L. That would linearize the data. So when you do that, you get all these terms here, and I don't show my actual data points, but it does work out to a line. And on a graphing calculator, on the AP test, you can take 2 points if you do. I shouldn't say you can. If you do take 2 points and random points and use those to find the slope, you'll get credit for using the slope to find the answer, which is, I'm getting ahead of myself because I'm talking about part F now down below, which isn't on the screen right now. But you won't get full credit unless you use the slope of a best fit line. The reason is that if you use your actual data points from the lab, the actual data points, unless they lie directly on the best fit line, they don't accurately reflect the relationship between the data. Your best fit line is a best fit line because it best represents the relationship between those two variables statistically. So you want to use the slope of a best fit line either from a graphing calculator, or if you happen to have 2 points that might happen to lie on that best fit line, they would accept that. Okay? So again, I'm getting ahead of myself because why do I need to know the slope? Because part F asks you to, using the graph, obtain the height of the tube. I want to leave everything I wrote here up, so I don't want to erase my whole ink here. Obtain the height of the tube, h, given that the mass of the dart is 0.02 kilograms, that's 20 grams, and the constant force is 2 newtons. Okay? Well, what does the slope represent? Remember, it was x, the slope is rise over run. My rise is delta x squared, my run is L. Okay, so delta x squared over L is my slope. And I know that that is 61. That's a measure of 61 from over here. So I'm going to use this whole relationship right here, H equals mg delta x squared over 4FL to get this answer. Oops, delta x squared. My delta x squared over L is 61. That's this right here. My m is 0.02 kilograms. I've got that. My F is 2 newtons. I've got that. And G, I could use 9.81 or 10 would be fine as well. Remember, it's the magnitude of G, not the sign. So M is 0.020. G is, I'm just going to use 10, sorry. I just said not to use negative, and I did. 10 times 61, that will be my delta x squared over L times 4, divided by 4 times 2. So when I solve that, let me get that offline, I get the answer of 1.5 meters. Okay? So that's how you can use the slope to of the data after you've derived this expression up here. So we derived this expression from the work equaling the kinetic energy, and then we solved for H. And then we used the slope of delta x squared versus L. We used the slope of that, and knowing what the constant force was and knowing what the mass of the dart was, we could calculate the height of that table. Okay? If you have questions on this, feel free to ask before, after school, or in class. Thanks.